I'm Matt Adamec. I'm a graduate student at UNL, and I'm here on behalf of the Coffee and Coffee Casa teams to show you columnar analysis with Coffee. Now, my first part here is just kind of what is columnar analysis, but I think we've kind of already covered that today with the previous tutorials. So I think we can just kind of skip over this and go to what is Coffee. And I should also mention, if you want to follow along with this tutorial, there is an entry in the AGC tools repository for the Coffee workshop. Okay, so what is Coffee? We've already kind of seen we can do columnar analysis just with awkward and other kind of tools in this HEP scikit environment. But Coffee kind of builds on a lot of different parts of the analysis pipeline. One of the major things that Coffee adds is Nano Events, and Nano Events lets you add a schema onto your data, and that schema kind of imposes certain behaviors. So for example, you can get some nicer formatting for your data. We'll see that. You can add things like Lorenz vector properties to your data, so it has a physical meaning, and you can cross-reference certain fields. We'll see some of this later on. And on the other end, on the kind of output side, Coffee also adds a processor, which can encapsulate your analysis and kind of deploy it however you want it to be deployed. Here on Coffee Casa, we have Dask, so we'll be deploying it on Dask, but you can also deploy it locally with, I think there's two executors, Futures, which uses Python Futures, and then Iterative, which just kind of goes through your data chunk by chunk, and I'll explain what that means when we get to the processor section. Coffee also used to have a built-in HISTs library, but this is now kind of a standalone package. This is still heavily influenced by the Coffee HIST sub-package, so we'll include some talk about that today. And then lastly, Coffee has lookup tools, which let you do things like corrections. We won't be touching on this today because it tends to be very analysis specific. Okay, so again, we've probably already seen this today, but I was going to start off this tutorial with some kind of really basics of how to do analysis with awkward. And I think this might be useful if somebody missed the awkward tutorial earlier. So we'll just go through this really quick. First off, you can open a root or HTTPS file with uproot, and it will open as it'll open with kind of awkward array. You'll get this T tree, and our tuple that we're using for this talk is this Z to mu mu sample, and it has kind of a branch for each of these properties. And this is not a very pretty file, but we'll kind of make it a little nicer with our schema later on. For now, we're just going to be seeing how we can kind of manipulate it. For one, we can open any of these branches as an awkward array with this array function. And you can see that the structure of our awkward array is jagged. So there's, each of these elements represents a muons PT, because that's the branch that we opened. But you'll note that there's these subarrays, and each subarray has a variable amount of muons because each subarray represents an event, and an event can have any number of muons in it. And of course, if we look at another branch like electron PT, we'll see it doesn't have the same structure, because an event can have any number of electrons, but it's not going to be the same number as we have of muons, generally speaking. And since this is a Z to mu mu data set, we don't have very many electrons, and awkward can handle that. It just gives you empty subarrays. And just to kind of prove that each of these subarrays is indeed an event, we can see that the amount of subarrays in both our electron and our muon PT branches is the same. It's about 44,000, and that is indeed about the number of events in our file. Now, we can also count up the number of muons and electrons in each of these subarrays if we wanted. We just have to change this axis that we're referring to in ak.num. So ak.num kind of sums up, it gives us the size of our array, but our array is jagged, so there's several axes. Axis 0 is kind of the least deep one. It tells us how many subarrays there are. Axis 1 is the next deep one. Axis -1 is the most deep one. In our case, axis -1 and 1 are the same. And we get the number of electrons and the number of muons in each event. And we can sum those up. We'd expect not very many electrons in this data set. And since it's a Z to mu mu data set, we'd expect about twice as many muons. And that's pretty much what we get. We had about 44,000 events. We have about 92,000 muons. And we have about only 10,000 electrons. And then, we can select data kind of in the standard way you would in the event loop method or any other. You just do a conditional on the data, but this time we treat the array itself as the object we do the conditional on. And if we ask for, say, mu on PT greater than 10, we'll get a Boolean array that has the same shape as our muon array, but it's, it just has trues and falses depending on whether a specific muon meets this cut. And we can apply this, we call this array a mask, and we can apply it to our data just in kind of the standard Python list indexing method. You put the mask in square brackets and it'll apply it to our data. And you can see down here, well, we had, for example, in our first event, 3 muons, one of them didn't meet this cut, and you can see in the output, it is gone. And, we can verify this. We'd expect to have the same number of events. We'd expect to have fewer muons because we're down selecting the muons here. And if we count up how many muons we have and we look at how many events we have in the input and output, well, the number of events is still the same, but the number of muons has gone down. So that behaves as expected. We can also do selections on our events, and all that requires is that our mask has a shape where instead of a true and false for each muon, we have a true or false for each event. So it's a one-dimensional mask instead. So here we query, we want to select events that have at least one electron. And I've moved to electrons here because there's very few events that have an electron, so it's easy to see whether this selection works. So we have we do our mask to see events that have at least one electron. We get a lot of falses. And when we apply this mask in the same way to our electron PT array, we see that all the kind of empty arrays get kicked out, which is exactly what we wanted. And in this case, we're down selecting events. So we'd expect to have fewer events, but we're selecting events that have at least one electron. So we expect to have the same amount of electrons, and our size goes down. So we have fewer events, but our electron count remains the same. So this is kind of how you can do most basic cuts for an analysis. There are some more complicated operations that Awkward lets you handle, such as combinatorics. There's an analog to numpy.where if you're familiar with numpy. But Awkward is a huge package. It can do a lot of different things. I'm sure you saw a better tutorial early today over Awkward. I've also linked to some other tutorials in the appendix at the bottom of this talk. So if you want to do something more complicated, I'd just refer to that, but this is sufficient for what we'll be looking at today. Okay, so let's move on to some actual coffee, since that's what this talk is over. And the first thing we'll look at, again, kind of on the input side of things, is Nano Events, which gives us that schema that helps us kind of better format our data. So we can open our file with uproot again, and we can look at the branches again. And if you'll recall, there were very many, I think 214. So I'm just looking at the muon branches in this case. And if we examine what these branches contain, there's kind of a lot of redundancy here. For one, this number muon branch tells us how many muons are in each event. But this n muon E branch tells us how many muon energies are in each event. And we'd expect that to give the same information because every muon has to have an energy. And so on and so forth for all these other n muon branches. And moreover, we'd expect muon E and muon PT while they don't have the same content, they have the same shape, because if there's an entry in muon E, then there better be an entry in muon PT. So naturally, we could kind of collapse all these muon branches into a single muon collection. If we scroll down a little bit, there's just a long explanation here about that's basically what I did. I created a schema specifically for this file. You can create a schema for any n-tuple file format. Schemas already exist for kind of the basic, the most common file formats, at least in CMS. We have things like Nano Events, and the coffea team also welcomes, if you need to make your own schema for some common file format, to submit that so that other people can use it as well. But again, I've just kind of made a schema for this specific file. And essentially what I've done is I've collapsed all our branches into these broader collection categories. So now if we look at the fields, and before I think for awkward, you have to do .keys. In Nano Events, it's .fields instead. We call these collections fields. And we see that instead of 214 branches, we now have about 9 on the kind of surface level view. Now, each of these fields, we can look into deeper. We can also look at their fields. And for example, the muon field has all the fields we saw above in the branches. So we haven't lost any data. We've just kind of reformatted it through our schema. Now, this is aesthetically nicer. And we can confirm that this is indeed the same as what we had originally. If we look at the number muon branch, which again tells us how many muons are in each event, and we can count up how many muons we have in each collection, and we see that it's the same thing. But kind of adding this extra layer of abstraction with this collection, there's actually natural interpretation for it in HEP, because the kind of most common operation we would expect if we take one muon and we add it to another muon is that it behaves kind of as a Lorenz vector. We add the two vectorially. And with this Nano Events schema, we can indeed do that. And it's not too difficult to implement that behavior. So again, I've implemented it in our case for our schema. And if we select a single muon object and we add it to another muon object, then we see that they add together. That's a valid operation now, and it results in a Lorenz vector. And this Lorenz vector has kind of all the standard Lorenz vector methods attached to it. So for example, we could do something like delta R to get the Euclidean distance between these two muons. We could look at any of these other properties that aren't necessarily in our data set. So for example, if we wanted mass, that wasn't in our original data set, we had energy instead. But with this Lorenz vector formulation, we can just query that easily. So this Nano Event schema really makes our life a lot easier as we go into doing our analysis in the next step. And it can also do some other things that aren't necessary for our purposes. But again, if you want to do any of these things, just look at the appendix. There's other resources linked. One example of something it could do is cross-referencing. So if we look at our muon fields, we have this jet IDX field, for example, and we could cross-reference this with the jets branch just for easier indexing there. Okay, so we fixed up our data with Nano Events. And now we're going to move on to doing kind of a little basic analysis. Since this is a Z to mu mu sample data set, let's plot the Z-peak. And I chose to plot both muons and electrons. Really, we wouldn't expect to see anything from electrons because there's very few of them, and just by the nature of the data set. But it's the same operations, so why not? So down here, we kind of do selections similar to the basic selections we did above. There's a lot of anomalous muons and electrons with really low PT, so let's get rid of those. So we just kind of down select our muons and our electrons, make sure they all have greater than 10 PT. something I should note is once we do this selection, we no longer kind of have the nice, what I want to say is the first event in our muons array is not necessarily the same event as the first event in our electrons array because we've down selected these independently, but we're going to be considering these independently for our Z-peak. So it doesn't really matter that we've lost that shared indexing. There are ways to do this cut so that indexing is preserved if you need it. And then after we've done our PT cut, we just select events that have 2 leptons of the same flavor. So we select our dimuons. Dimuon events, just make sure that the event has 2 muons. Make sure that the charge adds up to 0 because if this is a Z decay, then the Z is charge neutral. So we'd expect 1 muon with -1 charge, 1 with 1 charge. Same goes for electrons. And okay, so we have our dimuons and our dielectron events selected. Now, remember from our schema that we can treat these as Lorentz vectors. So naturally, we can just we have lepton pairs in these events, and we want to kind of vectorially add those lepton pairs and then find their mass to get to the mass of our dilepton events. So the way to do that is it's kind of simple. We use kind of typical Python indexing, I believe. This colon just means select all, and this first index is along the events, and the second index is along the muon axis. So we select across all events the first muon and the second muon. We add them together. They're Lorentz vectors, so they'll add together vectorially, and then we just ask for the mass of that combined that vector sum. And of course, we do the same thing for electrons. And when we look at these arrays, we see that they've effectively been flattened because we've taken, we had 2 objects in each event, and we summed them together, took their mass. So now we would expect a flat value. And luckily, this muon, just looking at these muon values, they seem to be quite close to the Z mass, which is about 91.2. And in the electron array, we have a lot of nonsense. There's only 33 events in our electron array compared to 20,000 in muons. So it's about what we'd expect. Okay, and then all that kind of remains to do is to plot what we have in our results in a histogram. And as I mentioned, the hists package is kind of the default way to do this in coffea analyses. And the hists package can do, it kind of emulates a root histogram. So we need to specify, ignore that. We need to specify some number of bins that we want to kind of reduce all our data into. So I just chose 50 bins, and then we have to say, what do we want the range of our bins to be? Well, 0 is a natural starting point. Nothing can be negative mass, and there'll really just be a shrinking tail after a certain amount. So we can just stop it at 150. And we're almost ready to plot, but there's kind of one more step. We don't want to throw our electrons in with our muons. So we define this categorical axis, and this categorical axis basically just splits our data into a dielectron and a dimuon event group. And it kind of just stacks those histograms instead of plotting them in the same bins. And we're ready to define our histogram with these 2 axes, and we're ready to fill it. And then when we plot it, we see that nice peak around 90 as we'd expect for our dimuons. And we see basically nothing for our dielectrons. It's just this flat blue line at the bottom here because there's so many more muon events. So, yes, and the HISS package is capable of handling things like reweighting and other kinds of transformations of these histograms. Now, we've been working with a very small data set, right? We had only about 40,000 events, 44,000 events, I believe. Now, if we had a lot more events, then we would want to probably deploy our analysis on something more efficient than just locally on our computer. And coffee processors handle this very nicely. The kind of details of our analysis don't matter in terms of how it's deployed, as long as we stuff that into this coffee processor. Now, I want to drift down a little bit. Unfortunately, you're too zoomed in to see this whole processor, but we can cut off the import. Okay. So the structure of this processor is nothing too novel. Everything we saw above in our analysis, well, this is pretty much copy-pasted verbatim from above. We've just thrown our analysis into this process function within our processor. And then if we wanted to do like certain transformations, we can lump those into post-process. That's where you'd handle things like reweighting. But in our case, this is essentially just, we're encapsulating our analysis inside of this processor, and that's all we're doing with it. Now, what this processor does, if we scroll up to this map, so we send in some data into it, and it'll split, depending on what executor we use, it'll split that data up into chunks. And we have 44,000 events. I think we use a chunk size of 10,000 for our example here. So essentially we end up with 4 or 5 chunks. And just kind of by the nature of HEP data, all the events are independent, so we can send those chunks to completely different workers. Those workers can handle their chunk, and they can produce some kind of histogram. And then at the end, we can accumulate all those chunks together, and the end result will be, the same as if a single worker had done it, because histograms are kind of nicely additive in that way. It doesn't matter what order you add it doesn't matter how you split the data or what order you add it into the histogram or what order you add the end resulting histograms in, you'll still get the same histogram. And in kind of coffee processor lingo, that's because a histogram is what we call an accumulator, and there's other kinds of accumulators built into the coffee processor. For example, you could do a dictionary of histograms. If you want to end up plotting multiple histograms with your analysis, then you can go with a dictionary accumulator. You can have an array accumulator, all sorts of accumulators. They're in the documentation for coffee. And we're having some hiccups here with the server, I think. It's okay. So we have our processor defined. All that remains is to throw it onto an executor. And an executor is kind of what handles the execution of our analysis, right? So again, in our case on Coffee Casa, it's Dask. And we have this, well, I guess we do. So everybody who's running in an instance of Coffee Casa has this Dask scheduler over here. And the Dask scheduler kind of coordinates the workers. And it's located at this IP address. So we instantiate our scheduler in our code. We have to upload our schema to it because this schema is just a local file. So our workers wouldn't have access to it unless we tell the scheduler to give it to them. And then we run this, we run this line, which tells us we want to use the Dask executor at this scheduler. We want to use this schema. We want to use a chunk size of 10,000. We want to break our data up into groups of 10,000. And then we just run it. We have to specify file set and what the branch is called and what processor we want, what analysis essentially we want to run. And I think if I run this right now, it'll break because I got those errors. So I think I'm actually technically disconnected from the server, but I pre-ran this and I will run it again after I show this off after I restart the server. But in case things break down, I just want to confirm we do indeed get kind of the same graph after our chunks converge and give us their histograms and sum them up together. And it is indeed identical to what we had up here. So let me really quickly, if I can move the Zoom thing out of the way, let me try to actually run it. For that, I'll have to restart this real quick. Or maybe not.
It seems like we hit some timeout issues with the URL. Perhaps it would be best to like continue with the notebook then on GitHub, the evaluated one. We're currently looking into figuring out what happened here.
Okay, it looks like the whole thing is down. Okay. I believe I was finished with the notebook pretty much. There was just a couple of things I wanted to mention at the end, which were, columnar analysis is this kind of broader environment. So we have tools like ServiceX and stuff that we can use. And it's still a work in progress, but Coffee does have a ServiceX executor. So you can use ServiceX along with Coffee for data delivery. And then I just wanted to kind of reiterate the appendix at the end. If you want to dive into Coffee and you want to do kind of more complicated things than we looked at here, there's plenty of resources down there. There's plenty of resources for things like Awkward and the HIST package and stuff like that. And I would especially recommend, I think there's an examples, there's one bullet point under Coffee that I highlighted. It's the Coffee Casa tutorials repository, and that has, I think, a nice kind of buildup of difficulty for doing columnar analysis. And it even has a walkthrough for a kind of full analysis, so you can see how that would be done. But given these problems, I think that that's a nice conclusion. So if there are any questions, I don't see any right now in the Slido, but if there are any questions, feel free to speak up.
Thank you very much, Matt. Very nice to see the details here of Coffee. Thanks for providing this introduction, and we will see Coffee in action again also later today. There was one question about HIST, the HIST package being the recommended approach now for histogramming, which it is. It supersedes the earlier implementations that were available in Coffee. And then there was a follow-up question to that, which is whether there's a minimal version of Coffee that is needed in order to be able to use HIST. I don't know whether perhaps you or Lindsay or someone else can take that question.
Yeah, I don't know the details of that. I think Lindsay or Nick would.
Yeah, that's anything from Coffee 0.7. So all the recent releases should are all able to support HIST. So that's the only limitation. And I think you can go back even further. We just don't test it. But 0.7 is kind of the minimum where you want to be.
I also wanted to mention, Jim said in the Zoom chat that you could also query fields, I guess, instead of keys in Awkward. I didn't know that, so that's good to know.
Okay, thanks a lot.
Just a second, Nick, I saw you unmuting. Anything there?
7.2 to be exact.
Thank you.
Okay, great. But as a user of Coffee, I would also say I encourage people to try out later versions. There's new editions happening all the time, so yeah, check them out if you're using Coffee.